Okay, so am I audible? Am I audible?
Yes, sir.
Yes.
Okay,
Yes, sir.
Yes, sir.
right. So there is some network issue, we understand, because of the internet connection and all, but we are trying to resolve this issue very soon. So we'll start with the subject that is control system. Okay, I think. So in control system, I think in other part it is started. Yes or no?
Yes, sir.
Yes, okay. So you are a little bit familiar with the transfer function, what is poles, what is zeros, okay. Why we require this transfer function in control system. So this basic concept, I think it is discussed in the class in other part, okay. So I will take up this module 3, that is the stability criteria. So first of all, I will discuss that what is the use of this control system in electrical engineering. Anyone can tell, anyone can have any idea why you are reading this subject? Anything, any idea? Anyone can tell. That is, it may be wrong, it may be right, no issue. But what is your concept that why you are studying this subject? That is the first question it should come into your mind. Because before studying this thing, what is the application of this subject? Any guess? Or you have any idea? You can share, please be interactive.
Sir.
Yes, please.
Hello. Sir, to get controlled output from any system.
Correct. Controlled output from any system. Now, let us say physically, if we want to understand that you have a system and you want to control it or something like that. So in that case, what is the meaning of that? Means, let us say sometimes in the control system, we are discussing basically whether the system is stable, unstable, okay. Where is its application basically? Really, in the practical field, we generally we accept this kind of thing when let us say in any industrial application or any kind of application. Do you have any idea on that? Any engineering application where we actually really apply this control system?
Sir, it is used in plants or
yeah, in the plant. This plant we are normally used to apply this control system. Any other places?
sir, where conveyors and rollers are situated, sir.
Yeah, conveyor belts, rollers. Okay. See, in every power plant engineering or power plant, we have this application of the control system. It is implemented everywhere. Okay. Now, apart from that, in the robotics application or in any let us say space research application or any kind of engineering problem, wherever you have a machine, you have a system. So there we need to understand that the application of the control system is obviously it is there. Okay. So wherever you have this kind of thing, so we need to see, let us say in your household purpose, you have a washing machine. Do you think that control system is there?
Yes, sir.
Yes, that is there. So everywhere, if you find any engineering appliances, so definitely there will be a control system. So the being an electrical engineer, you should know that what is the basically how we are going to control this particular system so that the system will perform its required performance within its definite zone. Okay. So let us say there are two kinds of thing we need to understand first this nomenclature before starting this chapter. So in control system, we are very, very familiar with the stability. Okay, so stability of a system. So stability means, let us say you have a, let us say, washing machine, and it should work in a fashion that if you are putting any let us say a number of clothes and you put some water, and it should basically it should rotate, and you will get basically washed cloth after some duration. Okay, and then you will put it into the spin or something like that, or if it is a automatic control, that automatically it will be done, something like that. So you should get a desired output, that wherever you have this kind of machine, you should have a, let us say, the finally the desired kind of output you are expecting. Suppose a robot is there. So robot, suppose the robot has to take some object from a particular location, and it should put that particular object from let's say location 1 to location 2. Now that is the particular object of that robot. Now if that robot is functioning within that particular its appropriate domain, then we'll tell that yes, the robot is functioning properly. Now sometimes it will happen that the robot is not functioning properly. So that non-functioning of this particular any machine, any electrical appliances or any kind of system, when it is not functioning properly, so we need to understand that there are some malfunctioning of that particular equipment. Now that malfunctioning of the equipment or appliances or any system, it is due to the parameter which are actually governing that particular system. Now, when it will govern the parameter of any system, there may be some input and there will be some output. So any control system, it has something which is interrelated. You have some input, then there will be a system, and then there will be some output. Okay. So for a particular input, the system will process that input and it will finally give the output. Okay. So this process should continue in a regular fashion, or it should be a kind of thing which is a regular, or it should be the routine matter of that particular system. Now, any deviation on this particular parameter of that particular system, that means the system is not functioning properly. So when any kind of system or any kind of let us say any appliances or any electrical machines or any kind of engineering application where you have some desired output and you have some input. Now based on this a kind of input, the input may be again a various kinds of inputs will come. We'll understand in detail later on, but first we'll understand what is the meaning of this. So the input will be processed based on the parameter of the system, and then finally we'll get the output. So if there is any such kind of deviation within the system, we'll understand the system is not functioning properly. That means system is going beyond the stable region. Okay, so the stability of any kind of system, it is basically the behavior of the system or the characteristic of the system which actually we want that the system should function as desired. Okay, so in this particular chapter we will understand that what are the various kinds of stability criteria which is actually in application. So those applications, how we are going to find out the stability of the system, so those things we'll discuss in this particular chapter. Anything, anyone's asking some question? Okay, so first the introductory part, that is the we'll just go through this particular topic. So an important requirement for a control system is that it should be stable. So any system, whatever may be the type of system, we want that the system should function in a stable fashion. So this means that if a finite sized input is applied to the system, then the output should also be finite. So then that means For a finite input, there should be a finite output. That means the corresponding to the input, whatever output you desire, that means from the external system, but whatever we desire, that we should get it. Now, an unstable system will cause the output to increase or decrease without limit. So that means any unstable system, it means the behavior of the system will be, it is uncertain. We don't know the system, whatever output we should get, either it will increase or it will decrease. So that means there is a change in the output. Whatever, suppose you have an input and you should get output is, let us say, 4 ampere. For example, the current should be 4 ampere, but you are getting the current is 1 ampere. So that means it is not correct. Similarly, if you are getting at the output, the current output is, let us say, 8 ampere. So it is not also correct. So you should get 4 ampere. So that means it is deviating from its the desired result. So then we'll say that the system is unstable. So anyone has any doubt on this particular question, that whether how we can differentiate a stable system and unstable system? Any doubt? Any question?
No, sir. Please continue.
Okay. Okay. So now we'll have. Now next is the condition for stability. Okay. So condition for stability. A LTI system is said to be stable under the following condition. What is the LTI system? It is linear time invariant. So system should be linear. Linear means it should follow that like y equal to mx. Okay. So it should be a linear type of system. Time invariant. Time invariant means with respect to the time, the parameter should not change. It is a linear system with all the parameter is fixed with the time. Okay, so there is no change of the parameter, system parameter with respect to the time. So then we can, what are the conditions based on which the system should be stable? Number one is a bounded input results bounded output. So you have a fixed set of input and you are expecting that your output should be a fixed set of output. Okay. Now, second is that if the input to the system is 0, then the output is 0, irrespective of the initial condition. So this is very, very important. So you have an input and then you have an output. So we need to understand that with respect to the input, there should be some output. So if we are switching off the input, the output will be, obviously it should be 0. There should not be some external input, or if at all there is an initial condition on the system, so that will not be basically affect the system output. So what are the different kinds of stability? What are the various kinds of stability? First is the absolute stable system, then second is the conditional stable system, and third is the marginal or critical stable system. Now what is the absolute stable system? Absolute stable system means, see, any system when you are using, so there we need to understand that it depends on the system parameter. So obviously the input and output, it always depends on the system parameter. System parameter means what are the basically parameter which is governing the system output. Okay, so those parameters are very, very important. So if you tune those parameters, it may so happen the system will be out of bound or out of the stable region. Okay, but in absolute stable system, if you vary this parameter, the system parameter, in all cases, we'll understand that there will not be any change in the system output. System output remains within the stable region. Okay, so those kinds of systems are basically known as the absolute stable system. Then second is the conditional stable system. Conditional means there are certain range. On that particular range, the system is stable. Outside that range, the system is not stable. So it is basically a conditional stable system. So here the system is stable for certain range of system parameter like k equal to from 0 to 100. For example, let us say k is a constant, gain constant, for example. So in that case, we will say the system is stable, but it is with some condition. That means it is stable within certain range. Then third kinds of system is the marginal or the critical stable system. critical or marginal stable system means if for a bounded input, the output maintains a constant amplitude and frequency of oscillation, such system is known as the marginal stable system. So let us say you have some input. Now in the output, you are getting the amplitude of that particular output is constant and frequency of oscillation is also constant. So in those cases, we'll say the system is marginally or critically stable. Okay, so in control system, basically broadly, the stability is basically classified into three kinds of stability. First one is the absolute stability, then the conditional stability, and third one is the marginal or the critical stability. If you have any question, you can interrupt me at any point. Okay, so we can discuss that particular point. Now, next is the stability with respect to the location of the poles and zeros. Do you have any idea of the poles and zeros?
Sir. Sir.
What is? Yes, please. What is?
Sir, I was asking about sir third stability system, sir. Third type of, sir, marginal type, sir.
Marginal. Yeah. For example, I will show you. Just a minute. Whether this one is visible, whiteboard is visible.
Yes, sir.
Yes, sir.
So let us say you have let us say this is the coordinate, XY coordinate. Okay. Now you are getting something, the response is something, it is a fixed kind of thing. Okay. A sustained oscillations. The system response is this kind of thing. So the amplitude is more or less fixed. You see, the amplitude, it is more or less fixed, and your frequency is also fixed. So if your amplitude and frequency, the amplitude is A. So this amplitude and frequency, both the things are fixed, then we'll say the system is marginally or critically stable. That means if you change a small parametric change on the system, so immediately that will happen, that the system will go out of the synchronism. So now it is clear? Now it is clear?
Yes, sir. Yes, sir. Clear, sir.
Okay. So now, okay. So now we'll come to this point, that what is the poles and zeros. So any idea on the poles and zeros of any system? Please tell me. Any idea that what is pole, what is zeros of any control system or any transfer function, basically. Rather, we'll say that poles and zeros, it is coming in a transfer function. So can you please tell what is poles and zeros? Anyone?
Sir, solution of denominator are poles and solution of numerator as zeros.
Very good, very good. So basically, when we have basically a transfer function, now if we equate the numerator of the transfer function to 0, then whatever solution we'll get, those solutions are the zeros of the system. Okay. Similarly, if we equate the denominator of the transfer function to 0, then whatever solution we'll get, that are basically poles of the system. So this is the basically broadly we can say this is the definition of the poles and zeros of any control system. Now we need to understand that what is the how it will affect the stability with respect to the location of the poles and zeros. So really these poles and zero will affect anything on the system, or it is basically for the only for the calculation sake. See, this is very, very important. See, control system.
Excuse me, sir.
Yes.
Hello, sir. Sir, explain it again, sir. I can't understand. Poles and zero.
Poles and zeros. Okay. I will.
Poles and zeros. Yes, sir.
Yeah. I will just again discuss. So let us say you have a transfer function. Hello. আমি ক্লাস নিচ্ছি, ঠিক আছে আমি ওটিপি দেখতে পাঠিয়ে দেব। So GS equal to, for example, GS equal to, let us say 5 into S plus 5 divided by S into S plus 2 into S plus 3. So let us say this is a transfer function. Now you need to calculate what are the poles and zeros of this particular system. So if we equate the numerator of the transfer function to 0, numerator of the transfer function to 0 means S plus 5 equal to 0. So S plus 5 equal to 0 means what is that? S equal to how much? S equal to minus 5. So this minus 5 is the zeros of the system. This is basically zeros of the system. Okay. Now similarly, if we equate the denominator of the transfer function to 0, if we equate the denominator of the transfer function equal to 0, then whatever solution we'll get, what are the solution? S equal to 0, then S equal to minus 2 and S equal to minus 3. These are the basically poles of the system. Now it is clear?
Yes, sir.
Yeah. Okay.
Yes, sir. It is clear.
Okay. Okay. So the CLTF. So CLTF, we need to understand that is the closed loop transfer function. I think it is not yet discussed. Whether open loop and closed loop it is discussed in your class. What is open loop transfer function? What is closed loop transfer function? Whether it is discussed in your class?
Yes, sir.
Okay. So closed loop, if there is a feedback, if there is any feedback in the system, that means from the output to the input, if there any feedback is connected, then we'll say that system is basically a closed loop system. So here a transfer function is given. The closed loop CLTF means the closed loop transfer function. Closed loop transfer function GS of a system can be in general represented as GS equal to K into S plus Z1 into S plus Z2 plus dot dot up to S plus Zn divided by S to the power n into S plus P1 into S plus P2 plus dot dot S plus Pn. Now here the values for S for which the numerator of the system transfer function is equal to 0 are called the zeros of the system. So just now I have described this thing. This is basically the definition of the zero. And similarly, when the new denominator of the system transfer function is set equal to the 0, then the values of S obtained are called the poles. So this is the basically definition of the poles and zeros of the system. Therefore, the roots of the numerator. So what are the roots? This when we equate this to 0. So S equal to minus Z1, minus Z2 up to minus Zn. So minus Z1, minus Z2, minus Zn, these are called the zeros. And similarly, if we equate this to 0, so this S will be 0, S equal to minus P1, minus P2 and minus Pn. So these are all called the poles of the system. So this way actually we can calculate the we can have in the we can calculate from the transfer function. Now we need to understand how we can actually calculate the poles and zeros and how we can calculate we can plot in the S plane. So we'll come gradually. Okay. So S plane is used to graphically represent the location of the poles and zeros of the transfer function. So like your let us say XY coordinate. Okay, then you have a r theta coordinate. Okay, in let's say in a complex number, we normally used to represent those things in the r theta form. Okay, similarly, normally in the Cartesian system, we plot it in the XY plane. Okay, similarly, we have a S plane. S plane means it is a S domain. Okay, S domain means it is similar to the complex plane. Okay, real axis we have that means along the x-axis we have the real values, and along the y-axis we have the imaginary values. Okay, so you normally these zeros and poles, they may be actually the complex number also. Okay, it is not always true that the poles and zeros will be always real number. Okay, so there may be some complex number also. So in that case, those poles and zeros will lie anywhere in the S plane. Okay, so we need to understand that is basically it is a plot that how these poles and zeros are lying in the S plane. So let the transfer function be 1 by s square plus 2s plus 5. So here the poles are calculated like -1 plus minus 2j. So could you please calculate whether you are getting poles equal to -1 plus minus 2j? Because what has to be done? This is s square plus 2s plus 5 equal to 0. Okay, then you calculate s. It is a quadratic equation, so you apply that Sridharacharya rule. Okay, so you please calculate. All of you, please calculate. Whether you are getting this value or not, please check. Are you getting this value?
No, sir.
You are not getting.
Not real value, sir.
It is imaginary value, but are you getting this value?
Yes.
Are you getting this value?
-15.
Yes, sir.
Okay, so this way you are supposed to calculate the poles and zeros of the any kind of system. Now let us say again you try for this. Okay, let us say the transfer function is gs equal to 1 by s square minus 2s plus 5. Okay, so calculate the what are the poles are there. Similarly, you equate this to 0 and cross check whether these poles, these values are equal to +1 plus minus 2j or not. Cross check. Because first you need to understand how to calculate poles and zeros of any transfer function. That is very, very important. Are you getting?
Yes, sir.
Okay, fine. Okay. So now you see there are these poles and zeros. After calculating these poles and zeros, we are supposed to plot in the S plane. So I have discussed what is S plane. So S plane, it is basically it is a plane which consists of various location of the poles and zeros which is present in a transfer function. Now here you see this is a real axis and this is your imaginary axis. Now, depending upon the location of the poles and zeros, the response will change. Okay. So in control system, first, this is the thumb rule. Any poles and zeros, if it is lying on the right half of the S plane, the system will be stable or unstable. Any guess? If
The right hand means unstable or left hand is stable.
correct. So this is basically a thumb rule. If any poles and zeros, if it is lying on the right half of the S plane, then the system will be stable. A system will be unstable. And similarly, if any poles and zeros which are lying on the left half of the S plane, then the system will be stable. But it is not always true that if the poles and zeros, if it is lying on the left half of the S plane, there may be some chances of instability because of the parametric change of the system. Now we'll see that depending upon the location, let us say the poles are zeros, it is lying on the real axis, positive side of the real axis. So the system response will continuously increase. So if the system response is continuously increasing in nature, we need to understand the system is stable or unstable. System will be, if the response is unstable, system will be unstable. Okay. Similarly, you see, if it is lying on the, if the roots are lying on the negative side of the real axis, the system response will gradually die out. That means the system is going, it is under stable region. Here also see, if there are some certain imaginary poles or zeros are lying on the imaginary axis, system response will continuously rise in nature. It is continuously rising. Whereas if it is lying on the left half of the S plane on the imaginary axis, then the system response will gradually reduce. Okay. So this side it is increasing in nature, response. And this side, the response is gradually decreasing. So similar kind of behavior we can observe in the lower half also. Okay, here you see the system response is gradually reducing. Here it is continuously increasing. So this is the nature of the kind of system. Now stability with respect to the poles location. So just now I have discussed this thing. If the closed loop system poles are in the left half of the S plane with a negative real part, then the system is stable. So stable system have closed loop transfer function with poles only in the left half of an S plane. An unstable system has closed loop transfer function with at least one pole in the right half of the plane or poles of the multiplicity greater than on the imaginary axis. So that whatever we have discussed, that always this for the stable system, the poles are zeros. Normally it should lie on the negative real part of the system. Okay. Now let us say first this is the a system is given GS equal to 6 into S plus 3 divided by S square plus 2S plus 2. Calculate the poles and zeros of the system with respect to the transfer function. So quickly you calculate what is the poles and zeros of this transfer function. Quickly calculate.
So 0 is -3.
Correct. Very good. And what is the poles?
Poles are -1 plus -I.
Minus?
Sir, -1 plus -I.
Plus minus I. Okay. Okay. Correct. So -3 and -1 plus minus j. Correct. So this is the basically poles and zeros of the system. So if any, and now the pole zero plot. This is a very, very important pole zero plot of the system. So pole zero plot means first you have a -3. So -3 should be located. So this is the, see, we used to represent any zero by a circle sign. Zero means a circle. Okay. Poles means it is a cross. So 0 always it is represented in the form of a circle, and pole it is always represented in the form of cross. Okay. So S equal to -3 means here we have a pole, and then we have another we have a, this is a 0, and then we have poles at -1 plus minus j. So -1 plus minus j, -1, this is plus minus j, means one pole is here and another pole is here. So there are two poles. Okay, two poles, they are lying in the opposite side of the complex plane. Okay. Now, is it clear that how to plot this pole 0 in a S-plane? Is it clear? How
Yes, sir.
pole 0 plot? Okay. Okay. Now, this stability analysis in the control system is basically first attempt. It was made with the help of the scientists, that is the Raut, both the scientists Raut and Harwich. Okay, these two scientists, they actually devised this stability analysis criteria, and using this Raut Harwich criterion method, the stability information can be obtained without the need to solve the closed loop system. So initially, what is actually it is done, we normally have a closed loop transfer function, and from that closed loop transfer function we can calculate poles and zeros, and that poles and zeros we can plot in the S-plane. So people normally at that point of time, before this stability criteria was actually developed, people used to actually plot it in the S-plane, and then from there they actually infer that whether the system was stable or unstable. But this particular practice, it was not found good, or it is not always true that if you plot in the S-plane and if the roots are lying on the left half of the S-plane, that system will be stable. This statement is also not true. So in that case, what has to be done? There was a Raut Harwich, both the scientists, they have actually developed this stability criteria, and with the help of this stability criteria, we can actually determine, that is very easy. We'll understand this thing in detail. Okay, so this can be achieved by determining the number of poles that are in the left half or right half plane on the imaginary axis. So basically, what is the method? It involves two steps. First step, generate a table called the Raut's table and interpret the Raut's table to tell how many closed loop poles are in the left half plane and the right half plane and on the imaginary axis. So this process we'll understand, we'll discuss in next class. That is the basically today is the introductory class of the stability criteria. So we'll discuss in detail this particular topic, the Raut Harwich criteria. So any doubt, any question from your side? Any doubt?
No, sir.
Okay, fine. So I'll stop here. Now, what I want actually, the LMS is at this point, there is a problem. So I need to take this thing, snap basically what I will do, I will take a print screen. I will do that. Leakage. Yes. Okay.
हेलो सर.
Yes, please.
सर ऑफलाइन क्लास स्टार्ट नहीं होगा?
अभी कोई नोटिफिकेशन नहीं है, अभी कोरोना फिर से बढ़ रहा है. So there is no such notification from the government. Okay, if there is clear notification, definitely it will be started. Most likely you can expect in the month of December. We are planning for that. And if earlier we are getting some notification, definitely it will be started. Okay. Just a minute, I am taking your address. Now from the next class, what you will do, you make it a practice. All the name and your roll number. So your ID should be name and your roll number. Okay. Just like, for example, Prashant Rao. Okay, so Prashant Rao, and then E something, the whatever your roll number. So it will be easy for us to identify something like that. Okay, so next class you will make it a practice. Okay, so that easily we can identify that for your attendance. Okay, so thank you. Any query or anything? So we'll close that this meeting. Okay, thank you. I'll close this meeting.